Now that we have a grounding in probability, we can look at this amazingly important thing called the binomial distribution. The funny thing is, I'll have to wait till later to tell you what binomial means and what distribution means. First, let's get to the key point. It has to do with this kind of thing. The probability of exactly so many successes in so many tries. Like what? Like Biff. Biff has designed a new casino game. Okay, the casino game is like this. You pay $10, you get 5 6-sided dice, and you roll them all. This is what we call trials. N trials, 5 trials, because we're rolling 5 dice. Okay, so each dice is considered a trial. Okay. And now here's the idea. You pay $10, you get 5 6-sided dice, you roll them all, and if you can get exactly 2 6s, not 3, not 1, but exactly 2 6s, you win $50. And so that would be x equals 2, because we're trying to get exactly x successes, and in this case 2 successes. We're rolling 5 dice trying to get exactly 2 6s. That's the kind of thing that the binomial distribution handles. Now let's look at this for a second. You're going to pay $10. Come here, you're going to pay $10, and if you can get 2 6s, you're going to win $50. Does that sound pretty good to you? Does it sound like you might, like if you kept spending $10 over and over, you might actually make some money off this game? Well, just a fun fact, probability, the mathematical field of probability, was invented by this guy that made a fortune against the Paris lottery. Turns out back in the old days when they had lotteries, and I'm talking like, what, 1600s or something, when they made lotteries, they didn't exactly know what they were doing. This guy figured out that he could win money off the Paris lottery, and he did. So let's see if we can win money off of Biff. What do you say? What do you say? So we'll answer these 2 questions. First, what is the chance or the probability of getting 2 6s on 5 dice? And does that mean that we're going to get a profit on this game in the long run? So we need to figure out what's the chance that we roll 5 dice and we get 2 6s, exactly 2 6s. So ask yourself, based on what we were doing in the last lecture, what sequence of events gets us to a win? Right? We have to roll 5 dice. Think of that as like doing 5 things. It's a sequence of 5 dice, 5 volts. What sequence of events gets us a win? And actually the answer is there's more than one way to do it, because you're going to roll 5 dice, right? 5? Yeah. So, I mean, you could get the 6 and then get another 6, and then these would have to not be 6s. They would have to be something else. You can't get another 6, but you'd have to have a 6, and then a not 6, not 6, not 6. But that would work. What's the chance of doing that? Well, the chance of doing that would be the chance of getting a 6 on a 6-sided die is 1/6. The chance of then getting a 6 on a 6-sided die is 1/6. The chance of then getting a not 6, well, if 1 is a 6, 5 of them are not 6s. And then to do that again is another 5 6, and then to do that again is another 5 6, right? So getting a 6 6, a something else, something else, something else in exactly that order, you can actually work out the probability of that happening. Multiplication rule, recall. And this comes out to 125 over 7776, and as a decimal that's like 0.016075. When you're working with these kinds of things, you might want to go with like 6 decimal places for now when you're calculating lots of different probabilities, because that's only one way to win. There's another way to win. Another way to win, let me get these arrows out of the way. Another way to win would be to get a 6 and then not a 6, but then get a 6 there and then not and then not. And what's the chance of that happening? Well, you'd have to get the 6 on the first try. Then you'd have to not get a 6. Not get a 6. That's a 5 6. But then you'd have to get a 6. That's a 1/6. And then you have to not and then not, so that's a 5 6 and then a 5 6. Okay. Now if you multiply those out, you may not be surprised to learn that we get exactly the same thing. 125 over 7776, which is about a 0.016075. So that's another way to win, to get 6s on the first and third throws. Or there's more ways. Let's try to list them all out. So I could get a 6 first, and then my 4th try. I could get a 6 first, and then last. Right? These are all winning combinations. Or I could miss on the first one and then get 2 6s. Or I could miss, get a 6, miss, get a 6, miss. Or I could miss, get a 6, miss twice, get a 6. Or I could miss the first 2 times, get a couple 6s. Or I could miss 6, miss 6. Or I could go like this, miss the first 3 and the last 2 are 6s. Whew, I think that's it. So how many of these are there? I'm going to switch colors now. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 different ways. So I'm going to go like this. 10 ways. And notice every single one of them is going to have this same probability, because I'm always going to have a 1/6 in there twice, and I'm always going to have a 5/6 in there 3 times. Now where they show up is going to be different, but there's always going to be 1/6 times 1/6 in there somewhere, and there's going to be a 5/6, 5/6, 5/6 in there somewhere. Multiplying in any order, right? You can multiply in any order, you'll get the same answer. And so what do we got here? We've got the probability of exactly 2 successes on the 5 rolls is going to be 10 times the 0.016075, and so that of course comes out to 0.16075. Now, in order to make sense out of that, I like to try to say, well, that means I'm going to win once every how many tries. So I'm going to go like this. Take the 0.16075. Any number can be put over 1, right? What I'd like to do is I'd like to solve for, I guess I don't want to use x really. What do I want to use? What do I want to use? Y, I guess. So, okay. This probability is the same as 1 chance in y. What's y? So you just do your cross products real quick like, and this ends up telling you that you will win once every, and it's just about 6 actually. It's like 5.98 or something. So a 1 in 6, one time in 6 you should win. You expect to win, which is kind of a loaded word, expect. I mean, it's not like you guarantee that you're going to win one every 6 times, but on average, over the long run, you should win once every 6 tries. You expect to win once every 6 tries on average. Okay, and you'll get 50 bucks. Woohoo! You get 50 bucks every 6 times you try. Now, how much did it cost you to play 6 times? Well, it cost you 10 bucks each time. So actually, you would spend 60 bucks to win 50 bucks overall on average over the long term. So I guess we're not going to make millions on this one. But see, that's how they get you. Of course, they rig it so that, you know, you're going to be winning often enough that you're going to get all excited and keep playing. But but you are gradually losing money. You are bleeding money to the casino. So anyway. So that's kind of what this binomial distribution stuff, and again, I'll explain what those 2 words are in a couple minutes. That's what it's about. It's about trying to calculate what is the chance I get exactly, in this case, 2 successes, 2 6s, out of n trials, 5 trials in this case. That kind of situation is the kind of situation we're looking at. Now, there's a big, huge thing here. Maybe I'll go to green because it is big and huge. Big, huge thing. There's a pattern that just happened here. So I'm going to sort of introduce a notation here, right? So this big P, this is a big P. Big P means probability of. That's what a big P means. And when you use this kind of a function notation here, P of 2, so the 2 is exactly 2 successes. And so this P of 2, what it means is, what is the probability of getting exactly 2 successes? Okay, that's kind of the nomenclature, notation, whatever you want to call it here. Now, this 10, you know where that 10 comes from? Well, we did it the hard way. We listed every single possible way of getting exactly 2 6s in 5 rolls. Normally, you don't have to do that. Isn't that nice? There's a button on your calculator that does that, wouldn't you know? And that button, well, you'll have to look for it. But it's on your calculator. It's the NCR button. On the Casio FX or so, whatever it is. My NCR button is, oh no, I got the wrong calculator out. Darn, let me run and get my calculator. Gotta get my calculator. So on the Casio FX 300 ES, here it is. So you know that big button that it's going to be a different color, green or orange or whatever, that has a big AC on it. The big AC button, below the AC button, the all clear button, you will see NCR sort of printed in yellow ink. You have to hit the shift key to get there. So you hit, in order to evaluate, in order to use this button, you would type a 5, and then you would do the shift button, and then get that NCR, and then you would hit the 2, and then you would hit equals. Try that. Try that. Grab out your nifty calculator. You paid $15 for it. You might as well get some use out of it. So 5, shift, NCR. Now there's another one called NPR. Stay away from that one. NCR. So 5, and your calculator is looking like this. 5, and then it puts a big C there, and then you put a 2 there. So your calculator looks like this. And when you hit equals, you get a 10. You get 10. You get a 10. So 5 choose 2 is the 10. So that's this part of our formula. Now, what's this stuff? How did we get that stuff? We took the 1 in 6 chance of success, and we had to do 2 successes. Get it? In every single one of these, there was always a pair of 1/6, because a 1/6 is your chance of success, and there's 2 of them. And then to fail, to get a not 6, was a 5 in 6 chance, and you had to get 3 of those, right? Right, 5 dice total. Notice that these exponents have to add to 5, because we've got 5 trials. The exponents have to add to 5. I'm looking for 2 successes. That matches this number. And 3 is what you get when you go 5, take away 2. So anyway, that's the formula for this. So instead of writing it all out the long way, we could have calculated the chance of exactly 2 successes by making this kind of a structure here. And you do get used to it after a while. It's going to look a little weird at first, but again, I had 5 trials looking for 2 successes. Start with the 5, choose 2. Here's the chance of success. It's a 1 in 6. I'm looking for 2 of those, so you have to square it. Here's the chance of actually failing, not getting a 6. That's a 5 in 6 chance, and you need 3 of those because you're doing 5 total rolls. So you need 2 successes, 3 non-successes. The next thing you should do is you should actually try typing that into your calculator straight from front to back. So I'm going to do this right now. I'm going to do my voice cast or whatever of me hitting buttons on the calculator. So the first thing I do is I hit the all clear about 18 times. I hit a 5, shift, get the NCR going, 2, and then I'm going to say times, and I'm actually going to do a parentheses here. 1 divided by 6, close the parentheses, raise to the 2 power. I'm going to have to hit my arrow button so my cursor gets out of the exponent, comes back on the ground. I'll do a parentheses again, 5 divided by 6, close that, raise that to the power of 3, hit equals, and my calculator is telling me that this is 625 over 3888, which is probably right. Hit the SD button, your favorite button, and it comes out to, who'd have thunk it, 0.160751. Just like we got up here. Oh, I forgot the 1. Okay, 0.160751. Actually, there's a big bar over some of these numbers, so apparently there's a decimal that repeats forever. But anyway, this is our big thing for today, this formula. Now, I kind of tried to explain to you how the formula assembles itself, so to speak, but let me give you the actual full-out formula, the general formula for any case you want. Keep this handy. This is what you do for binomial distributions. Anytime you're rolling dice and looking for 2 6s, or flipping coins looking for a certain number of heads, or whatever, you're doing something over and over looking for a certain number of successes. What's the chance of getting exactly that number of successes? Well, that's what this stands for, remember. Probability of exactly n successes. Probability of what did I say? N? Did I say n? X successes. Probability of exactly x successes in n trials. We call them trials for some reason. I'm flipping the dice. I'm rolling the dice 5 times. N is 5. I'm looking for 2 6s. X is 2. Okay, that. You take the n trials, choose the x. That's, by the way, how you pronounce that. N choose x. That's how you say that. N choose x. And you take a little p. That's a little p. And little p is the probability of success. We're calling success getting a 6 here. Or we were anyway. Probability of success on any one trial. So on any one try, it was a 1/6. And you raise that to the x power, because that's how many successes you're looking for. And then q is what we call the probability of failure. So let's kind of go like this. Probability of failure. And the way you get q is basically 1 minus p. P plus q have to add to 1. 1 means something happens, and p and q have to, you either succeed or you fail. So q equals 1 minus p, and then this exponent is, well, n minus x. So basically these two will always add up to the n, because n plus n minus x adds up to n. Okay, that is our general formula, and we're going to bring that with us to the next page, where we do a more traditional, I guess you would say, binomial distribution problem. Okay, so anyway, that's the start of the show. And I know at first the formula looks like, what? But you really do get used to it pretty fast if you just really get your hands on it, get dirty with it, you'll be fine. All right, let's go to the next page. A pollster problem. This is practical, right? You're doing a survey of some sort. Now, just to make it a little easier, I made the problem smaller. So we're only going to survey 4 Iowans. It's kind of a small sample, but that's fine. So we're going to select 4 Iowans at random. The caucus is coming up Monday as I record this. And so here's a question. Who's going to caucus for Trump, right? Now, they're saying, or I just looked it up on Google, 52% of Iowa Republicans are supporting Trump. 52%. So if you were to select 4 Iowans, we're just going to keep the sample small. If you were to select 4 Iowans, Republicans, I guess, and ask them, are you going to caucus for Trump? Well, that's the question. How many will? What's the probability that none of them will? What's the probability that all of them will? What's the probability that exactly 1, exactly 2, exactly 3 will caucus for Trump? This is binomial distribution par excellence. Okay, so first I'm going to do the probability of none, because we don't need no formula for that one. We know how to do this one. So the probability that none of these 4 people are going to vote for Trump is, well, it's a 52%, 0.52 that they will. So that must mean it's a 0.48 that they won't, right? So if none of them will, that means this guy won't, this guy won't, the third guy won't, and the fourth guy won't. And there's a 0.48 chance of each. So if you want to get all fancy, you can say it's 0.48 to the 4th power. We're looking for 4 failures, basically. And I worked that out, and it's a 0.053084. Again, I'm going to use 6 decimal places. 0.053084, so like a 5% chance. Doesn't sound so bad, really. 5% chance that none of them. So we're also going to want to figure out probability of 1, probability of 2, probability of 3, and the probability that of all 4. Now this one's actually pretty easy to do too. All 4 are going to vote for Trump. That means you need the first guy, the second guy, the third guy, and the fourth guy, all 4 of them. The sequence of events that gets you there is the first guy says, yep, 52% chance. The next guy says, yep, 52% chance. The next guy says, yep, 52% chance. And the next, let's better have a girl in here, huh? Girl says 0.52. Okay, whatever. So anyway, it's a 0.52 to the fourth. And that comes out to 0.073116. So it's about a 7+ % chance that all of them. It's about a 5%, none of them. It's about a 7%, all of them. Okay, cool. So those are actually the easy cases. The cases in the middle, that's where I'm going to grab out the formula here. So I'm going to say recall the formula. The probability of exactly x successes is number of trials, n choose x, like this. Probability of success to the x power. Probability of failure to the n minus x power. And I'm going to use that here. What's n? N is the number of trials. It's how many people are we surveying or rather. It's a 4. So it's 4 choose 1. It's 1 because we're trying to get 1. So 4 choose 1. And the probability that the person's going to be a trumper is 0.52. That has to be to the 1 power because we want one of them to be a trumper. Probability that the person's not a trumper is 0.48. And these exponents have to add to 4, so that must be a 3. You could just say n minus 1 is 4 minus 1 is 3, but I always say, wow, they have to add to 4. So that's a 1, that's a 3. And you can push these buttons right now on your calculator. You can hit the 4C1 button times 0.52 times, and then do 0.48 to the 3 power. I did this already. I got a 0.230, oops, 0 again, 31. You see what the pattern is yet? Probability of 2. What are you going to do? There's 4 trials. We're looking for 2. 4 choose 2. Probability of success is 0.52, and we're looking for 2. Probability of failure is 0.48. If we have 2 successes, we're going to need 2 failures. You work that out. You just push buttons right away on your calculator. You put a 0.373801. By the way, don't write 800. It's 801. You want to always round your answers. Don't just cut them off. If it says 6 decimal places, round to the 6 decimal places. Don't just cut it off. People seem to cut off things these days. It's like, yeesh. Can you fill this one in yourself? Can you get the answer yourself? Why don't you give it a twirl real quick? Twirl it. Twirl it. All right, here we go. 4 choose 3. Looking for a trumper, 3 of them. Looking for a not trumper, 1 of them. Type that stuff all in. You should get 0.269967. Oh, and by the way, do you know what these should add up to? If this is every possible thing that can happen, you're surveying 4. How many are going to be for Trump? Well, it either has to be none of them, 1 of them, 2 of them, 3 of them, 4 of them. There's no other possibilities, right? This exhausts all the possibilities. And if it exhausts all the possibilities, it should be 100% total. Now, if I added these numbers up, actually I did, I came pretty close. I got 0.999999. Good enough, right? So you expect it to be 1 or 100%. 99.9999%. Let's not quibble. Okay, so this is a binomial distribution. Oh, and by the way, I promised I'd tell you what binomial distribution means. Distribution, this is when, let's see, a probability distribution, and there's different kinds, like the bell curve is a different probability distribution. A probability distribution means you spell out, that's a spell out all the probabilities for every possible outcome. It's like a table of values. This is a probability, well, not just that, I suppose. Back up. This whole thing is a probability distribution because it spells out We've got a certain probability of getting none. We've got a certain probability of getting 1. We've got a certain probability of getting 2, 3, and 4. Go away. That's a distribution, a probability distribution. Binomial. What's that mean? Well, this has to do with the n choose r and n choose x part. There's something called the binomial theorem, and we don't need to know that really. But like you could work out some numbers here, like 4 choose 0 is 1, because there's only one way that you're going to be able to choose none of them. 4 choose 1 is 4. Whoops. 4 choose 1. Come on, you. Come on, you. Come on, you. 4 choose 1 is 4. Because if you got 4 of these things, how many ways can you choose one of them? Well, I might choose that one, or I might choose that one, or I might choose that one, or I might choose that one. There's 4 ways to do that. 4 choose 2 comes out to 6. And 4 choose 3 comes out to 4. And it turns out 4 choose 4 also comes out to 1. Notice the symmetry here. It's big in the middle, and then that's a 4, that's a 4, that's a 1, that's a 1, and so on. Anyway, that's called binomial distribution type stuff. So we don't need to go into that at all. It was just the NCR button is where that word comes from. It occurs to me that I haven't answered the full question. So let's get a really cool color. Purple. Okay, I forgot this question. What is the probability that 3 or more will caucus for Trump? So let's kind of shove this in here. So the probability of 3 or more voting for Trump, what does that mean? That means the probability of 3 and the probability of 4. You know, you'd add up all the way to the end of your distribution. So 3 or more means, well, maybe 3, maybe 4. And so you add those two numbers up. You add those two numbers up, and I got a 0.343083. Cool. Okay, so this is a pretty good workout with the binomial distribution. Like I say, it takes a little getting used to because there's a lot of kind of parts to this thing flying around here. But you get your hand dirty with it, you'll catch on. It'll be like riding a bike. You'll say, oh, I'm getting it. I'm getting it. Cool. Okay, one more page of stuff here. A couple more concepts. The good news is this stuff's amazingly easy to calculate here. So we want to introduce an idea of, well, first let's introduce the idea of an expected value. What's that mean? Well, look at this problem here. Biff is flipping 100 pennies. And he's counting. How many heads did he get? By the way, this is a famous example of a guy that was stuck in a South African prison, and he had nothing to do, so he flipped coins over and over and over and did some probability work. But anyway, Biff flips 100 pennies and he counts the number of heads. How many heads should he get on average if he kept doing this? Like, how many heads would you get? And so I want to write it out this way. The probability of heads really is 50% on any one try, right? And so 50% of his tries should be heads, right? That's what that means. So if he's doing 100 tries, don't you expect 50% of 100 to come out heads? And that, by the way, would be 50. That's all we mean by an expected value. How many do you expect on average? Well, you expect, it's a 50%, and if I'm doing 100 tries, then I expect 50% of the 100 tries. You want some symbols? I'll give you some symbols. You could say the expected value is 50. That would work. Or you could also go like this, and you could say the expected value is 50. Mu actually stands for the mean. But you say, well, on average, he's going to get 50. So you could say E equals 50. You could say mu equals 50. The formula, you want a formula for this? You calculate it this way. You say the mean is n times p. That's exactly what we did, ain't it? We took n, 100 tries, times p, 50%, or 0.5. 0.5 times 100 gave us 50. That's all this formula says. That's all that formula says. So you'll see this formula a lot, and that's all it says. So we expect 50. That's the expected value. Cool. Now, what's the probability that it actually happens, that he actually gets 50? See, it's kind of a funny word, I think, expected value. It's expected, but it doesn't mean it's going to happen every single time. We can actually calculate how often should it happen. What is the chance that we get exactly 50 heads on any one try? Go back to our binomial distribution formula. Let's do it in green. So the probability distribution formula says the probability of getting exactly this many successes is how many trials you got. Do an n, choose x. What's the chance of success on any one trial? Do that x times. What's the chance of failure? You'll have to do that n minus x times. Here, the probability of getting exactly 50 heads in 100 tries looks like this. 100 tries get 50 heads. Okay, that's 100 choose 50. The chance of getting heads, succeeding, is a half, and you want to do that 50 times. Turns out the chance of failing, in other words getting tails, is also 1/2, and you got to do that 50 times. Kind of an interesting formula. But if you crank this out on your calculator, you will get 0.079589. In other words, it's roughly an 8% chance. You go and you flip the 100 coins, you count how many heads, you only got about an 8% chance of getting 50. 50 is the expected value, remember, but it doesn't mean we expect it this time. We're only going to get it 8% of the time. In fact, 92% of the time, we're going to get something else. So that's something to keep in mind when we're using this word expected value. It's like, well, what do you mean by expected? What we actually mean is, but over the very long term, if we keep doing this over and over, if we flip 100 coins, count the heads, flip 100 coins, count the heads, flip 100 coins, count the heads, do that over and over, like maybe 20,000 times. If we keep repeating, things will average out to about 50 heads. I used to do this on Excel. I used to say, hey, let's have Excel flip 100 pennies for us, and then let's count how many heads we get, and then let's see how often, what's the probability of heads based on that. And it takes a lot of tries for it to come out to exactly 50%. So anyway, now here's the other question. See, in reality, and I need another color, back to purple. In reality, Biff will not get 50. He'll get somewhere between, well, X and Y stands for a lower limit and an upper limit. There will be some lower limit and there will be some upper limit. What will be the upper and lower bounds for 95% of his tries? Is this really purple? Whatever. See, sometimes, or not say sometimes, well, yeah, sometimes, he could get anywhere between 0 heads and 100 heads, right? I mean, that's what's possible. But how often is he going to get 0 heads? Not often. How often is he going to get 100 heads? Not often. Hardly ever. It's going to be really, really hard to flip 100 coins and get 100 heads. Really hard. What's usually going to happen is you're going to get somewhere between 0 and 100, right? 50 is what you expect. You're going to get, now remember, that was only an 8% chance, but it is your peak. You expect to get about 50 on average. You're going to almost never get 0 of them. And you're almost never going to get 100 of them. You expect some kind of like almost like a bell curve kind of a shape. You'll get 50 plus or minus, and we can define these upper and lower typical values here. What are they? Well, follow my formulas here. We have this one that we've seen before, mu equals NP. So number of trials is 100, probability of success is 0.5, so you get 50 is our mean. Standard deviation, and we'll see this more later, but standard deviation, there's a formula for that, and it's kind of a nice formula. If you've got a binomial distribution, that's your formula for standard deviation. Square root of NPQ, N is the 100, P is the probability of heads, and Q would be the probability of tails. Turns out that comes out to a nice even 5. And now to get the typical range, you do the mean plus or minus 2 times the standard deviation. That's your big set of formulas right there. And so what does that give us? Remember, that says 2 times the standard deviation. 2 times 5 is 10. So take 50 plus or minus 10, really. So we expect to get 40 on the low side to 60 on the high side. That's what we would expect. Not every single time. We will get 0 at some point. We will get 39 at some point. We will get 61 at some point. But 95% of the time, we're going to get between 40 and 60. So if you keep flipping the coins over and over and over, 95% of those times, the number of heads is going to come out between 40 and 60. That's pretty cool, right? I like that. I like being able to calculate that. Say, well, what am I expecting here? And you can not only come up with, actually the expected value is kind of a lousy thing because the chance of that happening is not very great. But the chance of getting between 40 and 60 is actually 95%. This is how we define it. Somebody said, hey, let's kind of say that 95% of it is between here and here. And it turns out it's plus or minus 2 standard deviations. In fact, that's kind of how they define standard deviation, I guess, in a way. But anyway, them's the formulas for this. I hope you enjoy it. I think it's time for some homework.